Hello everyone, we're doing physical science and we're looking at relationships. So make sure that you understand relationships, where they come from. We collect data from experiments and try and analyze the data and fit them into different types of relationships. So let's focus on exactly what we're doing here. So remember that there are various types of relationships. And these types of relationships specifically can be called either directly proportional or inversely proportional. And those have particular characteristics. So in terms of the types of relationships, directly proportional and inversely proportional. Now, each of these types have different ways of representing them. We can represent them in words, we can represent them in tables, we can represent them in graphs, and I suppose ultimately we can represent them as a formula or an equation. But we're going to limit ourselves to words, tables, and graphs for today, and we're going to take a deeper look at these particular relationships. So let's jump right into it. We recognize that when we have a directly proportional relationship, people will say that one variable increases, the other increases, and this is the important point here. It doesn't just increase, but it increases by the same proportion. What does that mean? This is too difficult to understand. No, it's not. If you double the one variable, then the other one must double. So in other words, when we say double, we mean multiply by 2. So if the one variable multiplies by 2, then the other one must multiply by 2. If we halve the one variable, that means we divide by 2. Then the other variable, the dependent variable, needs to change, and it will also divide by 2. And that's exactly what we're saying here. As the one variable decreases, we're dividing or multiplying by a fraction when we decrease something. The other one decreases by the same proportion, by the same factor. And the best way to see this is if we look at a table of data. Now, the particular experiment that I'm going to look at is in a simulation that deals with the extension of a spring. The force applied to a spring and how it will change the stretch or the extension of the spring. So let's quickly look at that. And what you can see at the moment, we have a mass piece at the bottom, which is applying a certain number of newtons, force exerted downwards. Look what's happening. As we increase the mass, we're increasing the extension, and we can tabulate that data to be able to see this increase in length. The increase in length, the extension, that's what we're talking about there. So I had previously used similar simulation, and I've collected some data. And what we can see here is I've changed from mass into Newton, and I'm recognizing that I'm looking at a force versus extension. When there was no force applied, notice there was zero force. Then the spring wasn't stretching any more than it would have. It was in the same original state. It wasn't stretched at all. But as I started to increase the force, notice that the spring increased. So we could say as the one variable, the force increased, the extension increased. But I want you to take a little bit of a closer focus here and notice a little bit more about what's happening here. Let's take this first reading. When we had a force of 1 Newton, recognized an extension of 2 centimeters. Now, if we double the force, in other words, we take that value and we multiply by 2, we'll get 2. And see what happens here? We take 2 centimeters and we've multiplied it by 2 to get the same amount. So each step it goes up. Notice this one has increased by, so if we multiply this one by 2 again, we'll go multiply by 2, and we'll go from 2 to 4. And notice what's happening here. If we multiply this by 2, we'll get 8. 4 times 2 is 8. Now, that's one way of looking at this sort of relationship. As we multiply by a certain number, a certain factor, it's going up in those steps. Now, what's important here is that we've got equally spaced steps. And there's another way to show this directly proportional relationship by looking at the relationship between how much has the dependent variable changed with respect to the independent variable. What are the steps? And so I just want to remove my scribbles there and show you that as we increased from there to there, we went up by 1. So the difference between here, the change in force, was a value of 1. And the change in extension, the change in E, was a change of 2. So the change was 2. And over here, the change was again a change of 1. The change in F was a change in 1. And notice here, the change is 2. So each time we went up by 1 over here, we went up by 2 over here. We went up by 1 over here, we went up by 2. This is another way of recognizing that there's a consistent change. And what's important mathematically here is that if we recognize that the force is the independent variable and the extension is the dependent variable, then we can say delta ext over delta f is going to be the gradient of the graph if we were to take these values and plot them. And if we got the same value every time, so it's 2 over 1 all the time, then we know that that gradient is going to be consistent. The only time there's a consistent gradient is if you have a straight line graph. So let's have a look and see. And there exactly, I've got for you the straight line graph. The gradient here is constant. But there's another thing that I need you to understand. The gradient, which we represent by m, it's a constant. It's not changing. So these steps are the same. The important thing I want you to notice is what's happening at the origin. Where the force was 0, the extension is 0. Now we can say this is a directly proportional relationship. And so when we look at it, we say, with directly proportional relationships, they can be increases or decreases, but they have to be proportional. Very important, the graph is a straight line that passes through the origin. And those are critical understandings for this term directly proportional. It's also important to recognize that if we change by a factor, when we say proportion, proportion means multiply or divide. I shouldn't have put up a 2 there, but let's just use the erasure and get it straight. So it's multiply or divide. If we are dividing by a number, we would be multiplying by a fraction. So the proportionality there is important to take note of. So please don't forget what this is about, and make sure that you've got a very clear idea of proportionality. Now, it happens that proportionality relates to those extensions of the spring. But we did an experiment previously about the pendulum, and we found that in the pendulum there were factors that affected the pendulum, and one of the factors that changed was the length of the string. And in terms of this, we have to ask the question, so is this a proportional relationship? Is it a directly proportional relationship? Well, if we go and have a look, we recognize as the one increases, the other increases as well. So that's looking very positive. If we look at the table of data and we say, well, if we went from 0.8 to 0.4, that factor that we've changed there is we've divided by 2. But if we went from here to here, notice that this isn't a divide by 2. If we were to divide by 2, that number divided by 2 would be about 0.9, and it's not 0.9. If we take 0.4 and divide it by 2, we'll get to 0.2. We take 1.28 and we divide by 2, we recognize that should have given us an answer of 0.64. So clearly, this doesn't look like it's directly proportional. Just because the one increased and the other one increased doesn't mean it's directly proportional. So if you look as well at the steps, you'll see that the steps are not the same. And we can do that very clearly. It's even better if we look at the graph. On this graph, you can see that the points don't really fall on the straight line. They fall above and below, and we've got a best fit line there. The important thing here is it doesn't go through the origin. There's the origin, the 0, 0 point. So this relationship is definitely not directly proportional. In fact, if we made it longer, we would find the points actually begin to flatten out. It doesn't carry on the trend line shown there. It actually flattens out. And so we can recognize that there are all sorts of relationships, and we need to explore them, but we have to depend on data to do that. So please make sure that you understand the conditions for directly proportional, and make sure that you analyze your graph correctly so that you've got a sense of when it is, even though if this gradient you might think is a constant gradient for this part of the graph, it might not be constant for the whole graph. You know what? I think it's time to take a short break. After this, we'll be looking at some further relationships, exploring the inversely proportional relationship. So join me for that after this break.